Yeah, sorry for my this one. Yeah. Are the slides now visible?
Yes, yes, it is visible now. Just
So,
make it full screen.
okay. Yeah. So is it okay now?
Yes, yes, please go ahead.
So I would like to begin by thanking the organizers for giving me the opportunity to present our work here. So this work has been done in collaboration with Professor B. Ravishankar at IIT Delhi. So this is
Sooryansh, you are not audible. You are not audible.
okay. So I think full screen mode is not working. So
It's okay. You can just share your slide and go ahead.
yeah. So just a minute. Yeah. So I will try to do here. Yeah. So this is the outline of my talk. I will start by introduction and some preliminaries which are
Your
required.
slide is not visible.
Okay. So I will try to, maybe some problem is there. Is it now visible?
Yes, I can see.
Not to me. Okay. If participant can see, then it's okay. But it is not visible to me.
Okay.
Can you move?
Sorry?
Yes, now it is visible. Just
Can you move your slides? Next. Yes, it's okay.
Okay.
it's
Thank you.
okay. Go ahead.
So I will start by introduction. So the first question with which we start is, what is the state of a quantum system? And the answer to that is, it depends on the experimental observation. What I mean by that is, suppose we designate some state as 0, but this state, if we do a complete quantum state tomography, this may be equivalent to a Bell state. For example, we see it in multi-electron atoms where we define some term symbol. And another example in quantum information where we see it is logical qubits. So 0 logical and 1 logical are the logical states, but they may be built out of physical multi-qubit states. So the point that we want to ask is that if there is a coherence in a logical state, for example, alpha 0 plus beta 1, when alpha and beta are not equal to 0, then there is an underlying entanglement in the physical state or non-locality in the physical state. So the question for today's talk is that how the conditions for non-classicality or coherence in logical systems related to entanglement or non-locality in the underlying physical systems. And we will show that the answer can be given by employing the tool homomorphism between stabilizer groups. So here there are two jargons in this slide. One is stabilizer group and the other one is homomorphism. I will try to explain both of them one by one. So we need the definition of a group. So a group is any set under an operation star that satisfies these four properties. That is, it is closed and there exists an identity inverse, and the group multiplication is associative. So as an example, consider the symmetry group of an equilateral triangle. So here there are 6 elements. The first one is rotation by 2 pi by 3 about an axis which passes through its centroid. So A will go to C and C will go to B and B will come back to A. And similarly, rotation by 240 degrees, in which A will go to this, C will go to A, and this B will go to C and A will go to B. And similarly, reflection about the three vertices, the axes which pass through all the 3 vertices. So this is the group multiplication table that one can construct very easily. So it satisfies all the 4 properties which we have listed there, that there exists an identity, that is the equilateral triangle is left unchanged, and for every element there is an inverse, and the group multiplication is associative. Okay. So, what is homomorphism? Homomorphism is any product preserving map between the two groups. So, for example, on the left hand side, if we have one group, so let us assume that G1 is we represent collectively as a set, and this maps to H1 under some map, and G2 maps to H2. Then the mapping will be called as a homomorphic map. Is if G1 star G2 will map to H1 dot H2, where this dot is the group multiplication in the group on the right hand side, and star is a group multiplication on the left hand side. So any product preserving map is called homomorphism. So we want to define this stabilizer group. Now this has been defined in a talk in the morning as well on quantum error correction with cluster states. So stabilizers are operators which have a given state as its eigenstate with eigenvalue +1. So as an example, consider this state psi L 0 + 1. So this is an eigenstate of two operators, identity and this Pauli X operator with eigenvalue +1. And of importance to us is that these stabilizers form a group. So this is the group multiplication table, and this stabilizers and its group is instrumental in quantum error correction, which was given by Peter Shor and furthered by Daniel Gottesman. So if we go to a 2-qubit state, so let us look at Bell state. So this is it has 4 stabilizers. So identity x1 x2 minus y1 y2 and z1 z2, and this is the group multiplication table. And this group is a commutative group, as one can see that the order in which one multiplies does not matter. So the most important thing for this presentation is that if we look at these two stabilizer groups, for logical state this and for this physical state, so there exists a homomorphic map. So this identity and z1 z2 can be mapped to logical identity, and this x1 x2 comma minus y1 y2, this can be mapped to xl. Now we will try to look at this second mapping more closely. Why this second map? Because this XL is an operator which detects coherence in the logical space. On the other hand, this x1, x2 and minus y1, y2, if we try to look at their nature, they are globally commuting operators, but they are locally non-commuting operators. So as I have said that it detects the coherence in the logical space. What do I mean by that? That one can construct a witness-like condition by implying this operator XL. So for both the incoherent state in the logical computational basis, it has its expectation value to be equal to 0. On the other hand, for this state psi L, which is the maximally coherent state, it has maximum expectation value 1. So from this observation, one can construct an inequality of this sort. Okay. On the other hand, if we try to look at a condition here, so both x1, x2 and minus y1, y2, they have this psi L as its eigenstate. So now we go to 3-qubit system. So we take an example of 3-qubit GHZ state. So this is the stabilizer group of 3-qubit GHZ state, which has 8 elements. Again, this group bears a...
Sorry, we cannot see your references below. So maybe you need to
so
zoom out little bit. Yes, now it is visible.
Yeah. Okay. So here it is, so this is the stabilizer group of a 3-qubit GHZ state, and this stabilizer group also has a homomorphic map with the stabilizer group of a single qubit logical state, in which this is the coset, which is, or this is the kernel of the homomorphism, and this is the coset which maps to XL. Okay, now the point is that again the same story, that this XL can be used for construction of a coherence witness, but the nature of this thing is important. Earlier those operators were detecting entanglement, but these are the operators which have been used for construction of Mermin's inequality. So I will go a little bit into what is Mermin's inequality and why these operators are used. If one multiplies these these four operators naively. So one will get a -1 because x1 is coming twice, y1 is coming twice, x2 is coming twice, and y2 is coming twice. Similarly, x3 and y3. So if they are classical numbers and this entire thing is consistent with the local hidden variable model, then at least two of them should have opposite signs. Only then the product can be equal to -1 because there are four of them. So one of them has to have an opposite sign. So this leads to this kind of an inequality that this sum is bounded by 2. One can check by giving or by assigning different values to them of the form 1 -1 -1 -1 or -1 1 1 1, that this modulus is always bounded by 2. Now, on the other hand, in quantum mechanics, the 3-qubit GHZ state gives an expectation value of 4. So this GHZ state maximally violates this Mermin's inequality. Okay, so the point is that now we want to relate both of them. That on one hand, we have a coherence witness, which is constructed by this XL, and on the other hand, we have these operators, which in this case are being used for construction of Mermin's inequality, or which in the earlier case were being used for construction of an entanglement inequality. So the point is that in order to do that, what one can do is one can start with a coherence witness or condition for coherence of this form in the logical qubit, expectation of XL greater than C, and one can replace this XL by a convex sum of its homomorphic images. So this XL will be mapped to some half of x1, x2 minus y1, y2. Now, why is it half and why not some arbitrary numbers? So that arbitrary number I have not shown here in the interest of time. Otherwise, one can play around and one can put arbitrary non-negative weights adding up to 1, like w1, x1, x2 plus w2 into minus y1, y2, and then depending upon the parameter space which is given by w1, w2 and c, one will get conditions for different non-classical correlations. But in this talk, if we put this c lies between half and 1, then this is the condition for entanglement, this x1, x2 minus y1, y2 greater than or equal to 1. So the point is that a condition for coherence gives rise to a condition of entanglement if one suitably uses the homomorphic images which are given by the homomorphism of two different stabilizer groups. So in a similar manner, if we look at the stabilizer group of a 3-qubit GHZ state, so this XL will be mapped to 1 over 4 and a convex sum of all the 4 operators which we have seen there, and this detects entanglement when C ranges from 0.25 to 1, and for C is equal to 0.2, 0.5, this is equal to, or this gives rise to condition for Mermin's non-locality inequality. So this we have tried for different, here I have shown only for linear entanglement and non-locality inequality. We have also tried for non-linear entanglement inequalities and quantum discord, that if one suitably uses the homomorphic images, then one can construct different conditions for non-locality, entanglement, quantum discord, etc., given a condition for coherence in the logical computational basis. Now, where is in this entire thing what we are always interested in, at what level the classicality paradigm is broken? So that paradigm is broken because of this thing, that a single operator XL maps to a number of operators. So there are non-unique resolutions, so in the form of these 4 operators, x1, x2, x3, and there are these things which are there. So the point is that a single logical operator maps to a number of operators which have identical, so I should go back to previous slide to explain this thing. So here all these 4 operators, they have identical action on this operator, on this state psi L. So a single logical operator maps to a number of operators and those number of operators are not consistent with any local hidden variable matter or separability paradigm. So this gives rise to this entire construction. So in conclusion, what we have shown is that coherence in logical qubits is a manifestation of non-classical correlations in the underlying physical multi-qubit systems, and we have generalized this thing to qubits as well. And an open question in this thing is that what about monotones? So that question is a bit tricky because the set of free operations in different scenarios, they are very hard to map. So that is still an open question. So thank you for your attention, and if there are any questions, you can ask.
Okay, thanks, Sooryansh. So questions from participants?
I have questions. So could you please once more explain the definition of monotones?
Okay. So for example, in the last presentation, that concurrence was being talked about. So monotone, so what I have shown here are the sufficiency conditions. So they are yes, no kind of conditions. Okay. But monotones on the other hand, they hierarchically organize the entanglement or non-locality. So for example, concurrence is a pure state entanglement monotone. So what I mean to say is that if you have a 2-qubit state like alpha 00 plus beta 01 plus gamma 10 plus delta 11, okay, so if you look at the quantity mod alpha delta minus beta gamma, so that thing increases as the value of that quantity increases, the entanglement in the underlying state increases. So monotone is, what do we mean by monotone? That it is, so there are certain conditions that it is zero for all free states, that is condition number one for a given resource theory, and it and it attains its maximum value for the state which has the maximal resource. So concurrence has the maximal value for Bell state, and then it is non-increasing under those free operations, meaning if you perform an LOCC operation on an entangled state, then concurrence cannot increase. Okay, so if function satisfies these conditions, then that function is called as a monotone. For example, concurrence.
Could you also explain what group theory has improved your calculation? What kind of operations were like simplified, or what benefits you obtained by using group theory?
Okay. So that is a nice question. So at which level group theory is coming? So you can see that here there is, so this psi L, this was like 0L plus 1L. Okay, so if one does not look at its underlying structure, then the stabilizer group, as I have shown in one of the slides, that is simply identity L and XL. Okay, now this state is that 0L plus 1L, if one defines 0L to be equivalent to the 000, and this is 111. So this is like this. So now the point is that here there are a number of operators. Okay, so now your question comes that how does group theory simplify or benefit in this thing? So what we will do is to try to look at all the homomorphic maps. Okay, so the question is that if we have a group of a lower cardinality, if we have a group of containing only 2 elements, then we will ask the question, okay, so how many groups are there, larger groups which bear a homomorphic map to this group? Okay, and then we will try to look at coset by coset. For example, I did not talk about this thing, and I did not mention the reason, but since you have asked that question, I will mention it. This is identity here, and all the elements in its coset, they are also locally commuting. Okay, so here we will not get any separable or any non-locality inequality which is solely constructed by these elements. So what we need is a coset which contains locally non-commuting element. And since we know that why is this kind of a structure coming, it is coming because the logical state is coherent. So we will try to look at all the homomorphic images which get mapped to this Excel. Okay, or in the higher dimensional system, this Excel square or Excel cube, and then so this group theory makes us this makes it easy for us to identify the operators which we should look at for construction of non-locality or entanglement inequalities.
Thank you. Could you show the reference which you used for? I mean, you mentioned some book on group theory, and it was not visible.
Okay, so this is the book on group theory by QIQT23. Okay.
Okay. Okay. Thank you. Thank you.
Okay, we still have some time for discussion. So if participants have any question, comment, he or she can ask. Okay, if not, so let us thank all the. Yeah, please.
Yes. Could you show the references which you used, because most of them were invisible because the size of your like slides.
This is QIQT23, and then the other thing. What one can look at is this Daniel-Gottesman thesis in the context of error correction. Okay, there this stabilizer formalism has been discussed in great detail. These two, or one can look at that paper which I have shown in the first slide, these two. So then in this we have put all the references.
Okay, thank you.
Okay, thank you.
Okay, thank you, Sooryansh, for this talk. So this is it from this session. So let us thank all the speakers for finishing their talks within time. So I think we will meet in the evening session, which will